C15, I want to conclude this chapter by talking about parity. Now, a parity transformation is one where x goes to minus x in one dimension. If you have three dimensions, like an x, a y, and a z, then to make a parity transformation, you would flip the signs in all three of those. But I'm only going to be talking about one dimension here. So suppose I have a differential equation. A second order differential equation is what I want to work with. Because in physics, these are so common, the second order differential equation. I'm going to pick one that's very, very simple. Let me pick here, y double prime. I think I'll pick the same differential equation that we've been working with here. Y double prime minus y is equal to 0. It's a homogeneous differential equation, second order. And if I write this equation out, I would have, say, the second derivative, like this, is equal to y. Now, what I would like to do is make a parity transformation on the differential equation. Let x go to minus x. And if I do that, I'll have the second derivative of y of minus x. And then here I would have a differential with the minus x in here with the square. And then I would have... Now, since the minus sign here would cancel, this differential equation is the exact same differential equation where now I have, instead of y of x, I have y of minus x. So we can think of our original differential equation here, if I just write it out with the x's, is this one here. So what this means is if I find a solution, y of x, to my differential equation, y of minus x is also a solution. So let's check that. Well, we know the solution to this differential equation here, where you take the second derivative and you get the same thing back. We know the solution. We've already worked it out. Y is equal to, a e to the x. That works. And I'll put a comma here. The other solution that works is e minus x with the b in front. And I'll put imply here, since I like to write the general solution as a e to the x plus b e to the minus x. So in other words, second order differential equation has two solutions. We found one because we know that a e to the x, when you take the derivative, you get the same thing back. You take the derivative again, get the same thing back. But then I can find the other solution by simply flipping the x, because I know that if I have a solution here, I have to have also the solution where x is minus x. So I could just immediately write down b e to the minus x. Well, you might say technically I should write down a e to the minus x, since that would be the flip, and you are correct. I could do that. That would be the other solution. But then remember, when we have two solutions, we can take linear combinations of arbitrary constants from in front. So therefore, I can write this as a and b, since these are different, can be different constants in general. All right, so now let's take another example. Let's take y double prime plus y is equal to 0, another homogeneous differential equation. And that would be the second derivative is going to give me minus the same thing back. Well, that reminds me of cosines and sines, because if you have, say, the cosine of x and the sine of x, let's look at these. If you take the derivative of the cosine and the sine is kind of easier for me because it's going to be positive. cosine. So we go ahead and do that one first. The derivative of the sine is positive cosine. But the derivative of the cosine, see, is minus the sine. So if you go with another derivative here, you have minus the cosine of x. You get the same thing back with a minus sign. And if you take this derivative, you'll get minus the sine of x. But the point I want to demonstrate here is that these are negative of each other. And since these are negative of each other, that's exactly what I'm looking for. You take the second derivative, you get minus the same thing back. So the solutions here, cosine, I can write down, say a cosine of x, an arbitrary solution. That's going to still work. If I put an a in front, the derivative going to still have that a there, and the derivative will still have that a hanging around. So I could put, in general, these constants in front, and then remember that for a second order differential equation, you get two solutions, and since it's linear, we're assuming now we're all down here, but linear differential equation, and this is indeed a linear differential equation because you don't see any y squares or any y times y prime. You see just functions of x at best in front of these. In fact, you just have constants. So therefore, I could write down a cosine of x plus b sine of x as a general solution. But the reason why I want to emphasize this parity and have this parity discussion is that I like to show you that when a differential equation is invariant under a parity transformation, which is a fancy way of saying if I replace the x's with minus x is in the differential equation has the same form, just has the y of minus x instead of y of x. When that happens, I can find solutions that are even and odd as my two basic solutions to the second order differential equation. In fact, with the differential equation that we looked at here, where you get negative the same thing back, immediately what popped out was an even function, and an odd function. Pop that. But with the differential equation that we did at first, where we have the second derivative giving the same thing back without the minus sign, then we got e to the x and e to the minus x using our trick where if you have e to the x, we can simply have a solution with e to the minus x, all right? And then take a linear combination for the general solution. But these are not even and odd. They have mixed symmetry. But watch this trick here. If we basically have an e to the x as the basic solution, removing the constant for now, and e to the minus x as the pair, the e to the minus x as the partner, then watch how I can make an even function. E to the x plus e to the minus x, I like to divide by 2. That's going to be an even function, f of x. And then if I do, for g of x, if I do e to the x minus e to the minus x over 2, this is an odd function. Let's go ahead and demonstrate that. If you let x become minus x, remember an even function, that has to bring back f of x, just like the cosine does. If you have the cosine of negative x, it's the cosine of x. Well, if you look at this and make x go to minus x, then a minus sign goes there and a plus sign goes there, but it's the same thing when you divide by 2 and add them together. It is the same thing. So that does check out. Now, when you have an odd function, say g of minus x, that's going to give you minus g of x. Just like the sine here, if you take the sine of negative x, that is negative the sine of x. All right, these are very, very easy to visualize when you look at here, say, if you come up here with some angle, theta, I'll call this theta here, then if you look at the cosine, that's going to be what's along the x-axis here. And if I had a negative theta, like down here, if I went theta down here, that's negative theta, has the same x component. While the sine of theta is this one here, but the sine of the negative theta, if I go below the axis, let's see, this could be a negative value. This is going to be negative because remember the point here and the point there, your x and y. Your x gives you your cosine and your y gives you your sine. And here the y is dipped below the axis, it's negative, but the x is positive. So therefore, here, if we want to look at this case to specifically see that it's negative, that it's an odd function, you put the minus x here and this becomes a plus x, and then you see, if you do that, you had e to the minus x and then minus e to the plus x over 2. You have negative of what you started with. To get this from here, you have to hit it with a minus sign. So that's the important thing I wanted to cover here, that to say this fancy way, if the differential equation is invariant under a parity transformation, that we can find solutions that are even and odd. Either they pop out, even and odd, like we saw that happen with the cosine and sine, or if they don't, we can simply construct them because one function that we get, we know that the other one's going to have the negative x. And then by doing this trick where we add and subtract them, we can then find the even and odd functions. This concludes our chapter reviewing concepts from calculus. And remember, if you're in this course where this is a part of, we do have to have some prerequisites, but you may be just a visitor, just coming in to just see this discussion on parity. So you're welcome to take the entire playlist if you'd like. We are deriving the Somiliana formula for normal gravity.